Continuing our lecture on multiple regression, we were introducing categorical variables and we foreshadowed about an interaction. Sometimes it's not reasonable to assume the effect of a variable is additive in the model, and just like an interaction term in ANOVA, we can test for interaction in regression. So we were working with this example of roller coaster data, and we were predicting duration from length of the track and a categorical variable of whether or not the roller coaster has an inversion. And so we graphed the two separate lines as if we split the data into two separate data sets for whether it had an inversion or not. And the top line, the red one with the X's for the data points, is for roller coasters with an inversion, and the bottom line for the blue circle data points is for roller coasters without. And we assumed it looked like there wasn't an interaction here. The slopes of the lines look fairly similar. The lines look fairly parallel. But we really need to check the p-value to determine whether there's a significant interaction or not between length and inversions. So in Excel, you can't just push a button to add an interaction term. Statistical software packages have this option, but in Excel, we have to manually do it. So I took the data set, this is just a small snippet of it, and you can see that I created a new column with length times inversions, and it's literally the length data point times the inversion data point. So the first observation in that right-hand column is a 0, and that's because inversions was 0. So 1235 times 0 is 0. The second one is 2423 times 1 for inversions, which is 2423, etc. So once you code this third column, which I just wrote a little formula for, then you can run the regression with that interaction term in the model. And I've copied the coefficients box down from that regression, and you can see that we have length, inversions, and the interaction term length times inversions now as predictors in our model. We can now see that the interaction term is not significant. The p-value is high, it's 0.63, and so we can assume that this is not a significant interaction. So what we do when we don't have a significant interaction, just like we did in ANOVA, is to remove it and rerun the regression without that interaction term using only length and inversions as predictors. So if the slopes are the same, the indicator variables can account for differences in the intercepts of the lines, but what if the slopes are not the same? We're going to work with an example on data from Burger King products, carbohydrates versus calories, and we're also looking at the variable meat. So whether the dish is a meat-based dish or a non-meat-based dish. And we can see from the scatter plot, the top line through the data points marked by X's that's in red are meat-based dishes, and the bottom line for the data points that are blue circles are non-meat dishes. And we can see that it looks like the slopes of the lines are different on this occasion. So how do we run our model? Well, we start just like we did before by introducing an indicator variable for meat. So we're going to call meat 1 if meat is present in the dish and 0 if it isn't. Adding meat to the model can adjust the intercept, but to adjust the slope, we've got to add that interaction term, carbs times meat. Notice that if meat equals 1, the interaction term carb times meat equals carbs times 1 equals carbs. And if meat equals 0, then that interaction term equals 0. So we run a regression with our interaction in there. Notice here in our output, under the variable column, we have carbs as one predictor, meat as another term, and carbs times meat as another term. So let's take a look at the p-values. The predictor meat is not significant. The p-value is 0.79, but the interaction term carbs times meat is significant. P equals 0.0012. It's really tiny. But since your interaction term is significant, you cannot remove the meat term from the model, just like we did in ANOVA. So that should be nothing new. So let's practice stating the regression equation. So how do you get the regression equation from your coefficients box? Well, you first get your intercept. Here it's 137.40 or 0.395. And then you take each coefficient times its variable. So plus 3.93 times carbs minus 26.16 times meat plus 7.88 times carbs times meat. And then we have our regression equation. So our estimated calories for a dish is 137.395 plus 3.93 times carbs minus 26.16 times meat plus 7.88 times our interaction term. So let's take a look at what it means for meat to be 0. Find the intercept and the slope. So we take our regression equation, which we just looked at a minute ago, and we plug 0 in for meat, anywhere it shows up in the model, and we get that calories, estimated calories, is 137.395 plus 3.93 times carbs, because those last two terms go away since they're multiplied by a 0. We can play the same game for meat equals 1, find the intercept and the slope. Again, use our regression equation, plug 1 in anywhere you see meat. This time, the minus 26.16 stays, because times 1, it just stays minus 26.16. So we combine the other constant, 137.395, minus the 26.16, and then we combine the 3.93 carbs to the 7.87 carbs, and it gives us 111.24 plus 11.81 times carbs. Now take a notice, when meat equals 0, the slope is 3.93, and when meat equals 1, the slope is much higher, it's 11.81. And when we take a look at our original scatter plot with the lines drawn in it that we started with, we can see that the slope for the meat line is much steeper than the one for the non-meat line. So this coincides. Some notes about interactions. We used a quantitative and a categorical predictor in our model, but I don't want you to be fooled. Interactions can occur between two quantitative variables too. And we'll look at examples like this. Now, if the interaction is not significant, what you do is remove it and rerun the model without the interaction. But if the interaction is significant, the terms in the interaction must stay in the model even if their individual p-values are not significant.